going to be a moderator for this talk. And welcome to Ask a Scientist with Abhilash Dumbara. He is a fifth year graduate student at Syracuse University and collaborator at the NOVA experiment here at Fermilab. The theme of today's session is the pleasure of finding things out, the science behind physics demonstrations. The activities are interactive, and you may unmute yourself and interrupt Abhilash at any point if you have a question. Or if you're not comfortable doing that, you can just use the chat on the middle right or left, sorry, on your middle left bottom menu. Um, we'll have also polls where you will ask you some questions. We'll ask you to guess what's going to happen in the experiments that we are going to demonstrate. Um, and we will eventually ask for volunteers to explain your thought process in the answers you gave. If you want to volunteer, you may just use the raise your hand tool that you can find on the reactions button on your bottom right. And with that, I'll pass to Ablash.
Hi everyone. So today is going to be fun physics demonstrations. Let me share my screen. Um, one sec. Yeah. So the title of the talk today is "Pleasure of Finding Things Out," and this is like the title is really close to me. I was when I was growing up, I was really inspired by Richard Feynman, and this is like one of his book. And the reason I like this book so much is in that he talks about like an incident when he goes for a walk with his father, and he sees a bird, and he asks dad what that bird is, and the dad was like, okay, so I'm going to teach you how you should think about learning stuff. So if I tell you, like, if this bird is called so and so in so many different languages, then it doesn't give you any more knowledge than what you have. Think about, like, what does the bird do, how does it fly? Like, those are the kind of questions. Like, knowing name of something doesn't mean you know something. So understanding how things work will what bring pleasure inside you. And I'm going to um, talk about that today. So, okay, heads up. So if you can gather these items but towards the end of the talk, that would be awesome. Let me show you what I mean. So I want, like, sheets of paper like this, just a sheet of paper, and scissors and a tape. Uh, so, and then a pen on which you can write. One sec, and also two sheets of paper which is cut like this. Okay, so next, so the way this talk is organized is I'm going to like show demos, but before I show anything, I will ask you to predict. So the whole point of physics is to understand why something happens. So I'm going to talk about four topics today, and the goal is to encourage you to think about the rules of nature and appreciate how science can answer majority of the questions, and I encourage you to question everything and think about why something happens, and why doesn't it happen in a different way, or what is the reason for something to happen that particular way. And so these are the four topics we are going to study today. First, we'll talk about mechanics. In this, I'm going to explain how how objects move, and what rules do they obey. And I'm going to talk about magnets and electricity. What is the connection between them, and how is electricity produced? Next, I'm going to talk about fluid dynamics. I'll start with talking about air or any fluids, and how eventually it will translate to how airplanes work. And this at the end, I have like a fun activity. Gather all the materials, and we can do some we can make a Mobius strip, and that is super cool. And okay, so now I will stop sharing the screen so you can see me. And yeah, so I will start with mechanics experiment. This is Newton's cradle. So can you guys see?
Yes.
Okay. So can I have the first question on the poll? So my first question is, what happens when I let go of one of these balls? How many balls will bounce out here? Let's see. Okay, that's nice. I see around 85%. Okay, let's check it out. So I am bouncing one ball. Yeah, the majority of people are right. So you hit the one ball and you get one ball on the outside. One ball goes in and one ball comes out. Okay. Now let's share the results. So majority of the people got it right. Now, next question. What happens? My next question is, what happens when I bounce two balls? When I bounce in two of these marbles, how many do you expect bouncing out? Two? Okay, that's a lot of people are predicting two. It's going down. Nice. Okay, one's got a tough competition. Okay, let's check it out. So I'm going to let go of two balls. What do you see? You see two balls bouncing out. Yeah. So majority of you are right. So you got 77% of you got it right. Okay. And next, um, my next question is, what happens when you bounce three of these balls? Three. Okay. So I see lot of few people are answering it as three. But think about it. There are only two balls left. How will it how will it be three balls bouncing out when I let go of three balls? Okay. So before I go further, I want to see when yeah, around 50% of you say 55% say three balls will bounce out, and 45 will say are saying that it there are two balls. Can someone who answered three tell me why there will be three balls going out? You can raise your hand or type it in chat. Momentum is conserved. Yeah. Right. That's a good answer. Uh, what else? Okay. I think we can try it now. Uh, so let's see. So you predicted there'll be three balls bouncing out, but I say even though there are two balls, how are three balls going to bounce out? Let's check it out. See, what do you see? You see three balls bouncing out? Yeah, yeah. So you were right. So the reason for this is I'm going to share the result. Stop sharing. Okay. So the reason for this is um, think about like it as units of energy. Like if I let go of 1, you'll get 1. When you do 3, the center one keeps switching between the left side and right side. So that happens because of law of conservation of energy, and momentum both. So the conservation of energy says energy cannot be created, not destroyed, but only transformed. So if I'm inputting 3 units of energy, you should get 3 units of energy out. So that's the reason for this. Okay, now next question. If I have to bounce 4 balls, what happens? 4, 4. Okay, okay, okay. Yeah, nice. Yeah, majority of you are saying 4 balls will bounce out. Yeah, that's what we expect to see, right? Because of the law of conservation of energy. Let's see. See, 4, 4, 4, 4, 4, 4, 4. Yeah, yeah. So this is called Newton's cradle, and I think by the end of fourth question, majority of you understand how law of conservation of energy works, and that is awesome. Now, give me a second. Let's see. Next, we have demos about electricity. So let me put this away. So now here I have like small pieces of paper. Can you see? So my question is, what happens when I take this balloon and rub it over my head and bring it near the pieces of paper? What happens? Paper gets attracted toward balloon. So we are getting many people saying, yeah, they get repelled. Some people are saying they just move around. Okay, cool. I think now it's time to check it out then. So majority of you answered right. So let's see. See? Yeah, you're right. So the pieces of paper are getting attracted to the balloon. So what is the reason for this? Can someone type it in the chat or raise your hand? Paper has positive charge. Static electricity. Yeah, so think about uh, like when I rub the balloon on my head, it is getting charged, as in some of the electrons are removed. I don't remember exactly if it is removed or added, but that doesn't matter. It has to have one kind of charge. So once it has one kind of charge, it um, it attracts the paper. Paper is a polar object. Yeah, yeah. Okay. So that is the demonstration to show you about the electricity. And next, let's see. I have this plasma ball. Let me turn it on. It looks really cool. So my next question is, what happens when I touch this plasma ball? Make your predictions. So science is all about prediction, right? Yeah. We want to know what, based on our current understanding, what happens in the future. And that is what all we are trying to do. I see someone said it explodes. Yeah, let's see. So I'm gonna touch it. See? Yeah, does it? So yeah, majority of you got it right. So let me try to explain what is happening in front of my board. Can you guys see my board? So when there is like an object with lot of charges, right? It wants to come out. It wants to discharge, but uh, there is air in between, and it has to have so much high voltage or high energy to break the air. And this happens when there is like a positive charge somewhere around, and then it can neutralize. And that is what happening when i touch I touch the plasma ball. um, so this plasma ball this plasma ball has like a air inside it, and my consider my hand is like a positive end, and when I touch it, I'm basically giving it a least resistance path for those electrons to flow. So that is the reason that this plasma ball like forms a lightning uh, when I touch it. Next, okay, let's see what do we have next. Okay, so next, I'm going to ask some questions about magnets. Magnets are super fun. I used to play with them all the time. When I was a kid, I still do. So, what kind of materials get attracted to magnet? Can I have some answers in the chat? Ferromagnetic materials, ferrous materials, metal. Okay, metals. Yeah. Now, iron, nickel, cobalt. So many of you are have got it right, but I have a plate here with uh, just water in it, and I'm going to put a cereal. So I have the cereal box. I'm going to take one cereal, put it over here. So is does magnet attract the cereal? Is cereal magnetic? Yes, yes, no, no. Okay, it's going about 50-50 now. Okay, so let's check it out. So I'm going to bring the magnet close to the cereal. See? Do you see it coming closer to the magnet? Yeah. You see how the magnet is getting attracted to the cereal. Yeah. So the reason for this, what do you guys think? What do you guys think the reason is? Can anyone like type it in the chat or raise your hand? Yeah, cereal has iron in it. This is the cereal I got. And if you see, yeah, so it has iron. It has like 12.6 milligram of iron. Yeah. So the food we eat, which has like iron, it's the iron which gets attracted to the magnet. Isn't that awesome? Okay, next. My next question is, what about copper? Does copper stick to magnet? So this is the copper. My question is, does copper stick to this magnet? So this is a neodymium magnet. It's quite strong. So if you guys deal with this, be very careful because it can like really pinch you. Yes. So we have 42% saying it does attract to magnet and 59% saying no, it doesn't. 61, no. Okay. But if you run through, yeah. Yeah. Some people are answering the question, which I'm going to show eventually. But yeah, that's nice to see many people know some of these concepts already. Okay, so majority of you don't think it doesn't attract to magnet. Let's see. Does it? No, it doesn't attract. So copper is not magnetic. Copper doesn't get attracted to magnet because copper is diamagnetic. That means it doesn't get attracted to magnet. But what it does, it can conduct electricity. That is something which will uh, you'll get to learn about it soon. Okay, next. Okay, next question I have is very simple. What happens when I drop this magnet? Okay, it falls down, it falls down, it goes up. Okay, yeah, so it's a simple question. If I drop this magnet, it just falls, right? Yeah. So, okay, yeah. So my next question is, what happens when I drop this magnet inside this copper tube? Can I have that poll question? Yeah. So my question is, what happens when, I hope you can see properly. Yeah. So my question is, what happens when I drop this magnet inside the copper pipe? It falls, but slower. It falls at faster speed. Okay. Let's see. We have many people saying it falls, but slower. Can one of you reason why? Give me the reason why it would slow down in the chat, or you can raise your hand. Okay, eddy currents. Yeah, it's not magnetic. Yeah, I mean, if it's not magnetic, then why does it still slow down? Like, it doesn't stick to magnet, but why does it still slow down? Lenz's law. Yeah, yeah. Yeah, I think some of you got the answers right. But remember, knowing Lenz's law, like just knowing um, the name Lenz's law, doesn't mean like you know how Lenz's law works. So focus, like try to understand the meaning and the physics why that happens. Then um, remembering the names, but yeah, you have to remember the names to convey to other people. So friction created, okay. Small tube, actually it doesn't matter what the size of the tube. Like if I take a bigger tube, it will be the same result. Magnets create electric field due to the movement. Okay.
I think that the reason there is that maybe if the tube is small enough, it's going to have friction between the magnet and the tube.
Oh,
Why it's
oh,
going.
actually it's not small enough. It's like, so if you see, it's not like really small. It still like goes in. Okay, so let's see what happens. So I'm going to drop a magnet outside, and I'm going to drop a magnet inside. So I have two magnets, one on right hand and one left hand. So let me start slowly.
Can you
If
lift a little bit more?
Huh?
Can you lift the tube a little bit more so we can see the bottom? Yeah.
Okay. So yeah, 3, 2, 1. Yeah, you see the one. Oh, you see the one which goes through copper is much slower. I'm going to demonstrate it again. You see,
Yep.
these magnets stuck together. They're very strong. So, okay. So I think at this point I will like to explain how this happens. So let's go back to the board.
Abhilash,
Huh?
there is a pertinent question in the chat now. So Neil asked it, how much warmer is the tube now?
That's a great question. The answer is, I mean, there is no way of for me to know, uh, except that if I touch it, it doesn't feel warmer. But the reason, uh, yeah, I understand your question, but I cannot measure with my hand. But I'm sure it is a bit warmer than before, and I'll explain that in a second why. So what happens is, this is the pipe, and say this is the magnet. I'm dropping the magnet through the pipe, right? So there is a law in physics called Faraday's law, which basically says moving magnet is same as current. So when there is a changing magnetic field, when the magnet is changing, the magnetic field on some space is changing, that will cause a current, an electric field. And also it's the same for the reverse as well, because if there is a current, so if I have a wire and if I
Uh,
pass.
Sorry, can you lift a little bit the angle of your camera because we can't see the top?
Oh,
Yes, that's good. Thank
uh,
you.
so this is a wire, say copper wire, and if I connect it to a battery and pass a current, this wire is a magnet. So whenever there's a current flowing to something, it becomes a magnet. Or if there is a changing magnetic field, then it forms a current. So what's happening here is, the changing magnetic field is producing the current which goes circularly around this copper. And that is the reason the copper will warm up, like Neil said. So, and that current which goes around produces a magnetic field, because the changing magnetic field, the changing magnet produces the current, and that current produces a magnetic field in an opposite direction. So if this magnet is north and south, the current produces magnetic, um, makes the copper magnet like this, north and south. So this north and north repels of the magnet. So that's why, because of some the eddy currents, that is called eddy currents, which pushes the magnet up, slows the magnet down when it falls. If you coated the tube with rubber and hook up the battery, ma- rubber. Had to think about this question. So with the rubber, I think there has to be a path for current to flow. And since rubber is not electric, like you cannot pass current through electricity, uh, I'm answering the question in the chat. So if you have rubber, then there won't be a path for electrons to produce eddy current. So that will just be like dropping the magnet without the pipe. Okay. I mean outside, so you could hold. I mean on the outside. Uh, okay, let me come back to your question later. It's a good question. Um, let me go ahead with other demos and I'll come back to that. Okay. So next, so that is about the electromagnetism, how moving magnet can produce electricity, which in turn can produce magnetic field, which opposes the original magnet falling down. Now I'm going to do a demo. So I have a wire and I'm going to stick this magnet there. And okay, so next poll question. What happens when I quickly move this copper pipe, like suddenly on this, near this magnet? What happens? Nothing happens. Yeah, I see the second and third option is getting a lot of answers. Yeah, okay, let's see. Let's see what happens. So I'm going to quickly move the magnet. See, I'm making sure that I'm not touching it. Sorry, give me a second. Yeah, you see the magnet is moving, and the faster I move it, the more the effect is. You see? Yeah. So, yeah. So what is the reason for this? Any answers? You sure it's not the wind from the movement? No, it's not the wind. So the reason for this, magnet creates electric field due to movement again. Yeah, yeah. So when I move the magnet creates the magnet creates current in it, and that current creates a magnet which repels that magnet. Does that make sense? Okay. So I have like few more demos to show. So let's move on. Next, we'll switch to Next topic, fluid dynamics. Okay. So first question I have is, does air has weight? So the air around us, does it have weight? Yes? No? So many of you are saying yes. So why do you say yes? Do you like feel air pressing you, or like if I hold this, like I feel the weight, right? Do you feel the same weight of air on you when you're standing? Yeah. So 97% of you say yes. The different elements have different masses. Any matter has weight. Yeah, right, right. Okay. So that comes to my next question. So I have a balloon here attached here and an empty balloon here, and this is towards the center, right? So what happens when I let go of this balance? The side with air-filled balloon goes down. Yeah, that's nice. Many of you are saying it's option 2. Okay, so yeah, let's check it out. Yeah, you're right. Yeah. So that's the right answer. So air, no matter if it doesn't feel like you have like weight on you, but air does have weight, um, just like from the experiment that you saw. So I want to talk about air pressure. Air pressure is, say, if I'm applying force on this table, I'm applying it over some area. So force applied on some area is called pressure. So when so I'm going to like explain about some of the fluid dynamics, but before that, we'll build up to that. So I'm going to ask my question. Okay, can I have the next poll question? So here I have a sheet of paper, right? Here I have a sheet of paper. So what I'm going to do is I'm going to blow air here on top of this. So what happens? Paper goes down. So in general, right? Like if I blow on this paper, like it just like wherever I'm blowing, it just goes towards that direction, right? Like if I blow this, it goes away, like in which direction I'm blowing. But what happens when I blow it like this? So many of you are saying paper goes up. Can you tell me the reason? It goes up. How that's how planes fly. Difference in pressure. Yeah, that's what I'm going to demonstrate. Moves it up. Yes, 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 yes. Yeah, great answers. So let's try. You see? Yeah, you see it's blowing up. So that is because of a relation called Bernoulli's principle. Basically, it says like if air is moving faster, the pressure is less. So if I am pushing the paper up and also pushing it down, it is at the same place. But if the pressure or the force on the above is less, the pressure here on the bottom is high, then it moves up. So that is the reason for um, what you see, for seeing what you see. Okay, next I have two balloons here. So can I have the next poll question? What happens when I blow in between these balloons? They move closer together. They move apart. Yeah, so if you apply the same principle from previous demo, what do you think? So many of you are saying they come closer together. There is a fight between they move apart and they come closer together. Okay. Are you excited to see what happens? Okay, let's see. I'm going to blow it on it now. See, let me push them a little bit apart. Right, they're still. I'm going to blow it on it, blow on it. See, they come closer together. So the reason for that is wherever there is fast moving air, the um, the pressure is less and the pressure outside is more. So that pushes them together. Okay. Now I have another demo, which is a fun demo, but you gotta be careful if you do it at home because it might cause.
Abhilash, this is just a warning. You have a minute for that one, okay?
Oh, okay. I'm just gonna do this one last thing. So I have a tea bag here. So what happens when I burn it? Burns, flies up. Yeah. Okay. So many people are saying it burns, nothing happens, and many of you saying it flies up. Okay. So let's see. Oh, the lighter is not working. Yeah, it is. Yeah, I'll just do one. Yeah, see? Be careful, don't burn down the house. You see? So the reason for that is whenever there is hot air, it's less dense and the pressure is less. So that's why the hot air always rises. It's not like hot air rises, but the cold air around it is pushing it up. So also because of the hot air, it's like raising, and also the tea bag is very, very light. So it just like when the hot air rises, it carries uh, the tea bag along with it, right? Okay, so next, okay, next, gather all your uh, strips of paper. Let's do a fun Mobius strip experiment.
There's one question, one last question in the chat. So Nina asked it if that's like a hot air balloon.
Yeah, it is. I'm going to move on because I want to finish all the things I planned, but I can answer more questions in more detail later. So let's start with the Mobius strip. Okay, now take your paper, take a piece of. So what happens? So what I'm doing is I'm taking a sheet of paper and I'm connecting them and I'm gonna stick a tape, right? So my question is, what happens when I cut it along this straight line? When I cut it, so this has two sides, right? Outside and inside, right? So if I draw on it, the outside will stay outside, and if I draw here, the inside will stay inside. So this has two sides to it. This is and now can I have the poll question? What happens when I connect them, when I cut it in the center like this? You get two strips of paper separated but entangled. Okay. So you keep guessing. I will. Yeah. So you get two sheets of paper. Yeah, simple, right? That's not very complex. Now, what happens when I do this? So I'm gonna take a tape. So now what I'm gonna do is, instead of connecting it just straight, I'm going to give it one twist and connect tape it here. Okay. So this is a Mobius strip, right? So how many sides does a Mobius strip have? So compared to this, it has two sides, but Mobius strip just has one side. I can prove it to you. So can I have the next poll question? So what happens when I draw on it, right? So let me see. I'm just going to draw on it. So, right, I have not lifted my hand at all. I hope some of you are doing this experiment along with me. See, now they meet, right? So I just draw one line and they met together. That means it has just only one side. That is like mind blowing. Okay. Now, next question. What happens when I cut this Mobius strip? So I'm going to start cutting and let you answer the question. Until then, of course, you'll get two papers last time, right? Yeah, yeah, that makes sense. Like, why should it be any different, right? So make a prediction. Yeah. Okay. I am almost done. Okay. Now I have cut this. Voila. Oh, sorry. It got disconnected. But I didn't stick the tape properly. But basically, you get one single loop. Isn't that spooky? Yeah. So this is like some weird properties about Mobius strip, and it's like geometrical. Yeah, it's just like very surprising to me whenever I do this experiment. All right. Okay. Next, we shall do. So I am now let's do the Klein bottle. So Klein bottle is like a 3D version of the Mobius strip. I don't have it with me, but like do check out some nice. There are like some nice videos about that in YouTube. Okay, next, what I'm gonna do is I have this plus shaped of paper, and what I'm gonna do is I'm going to form two loops, one here like this, like this, and the other side I'm going to form a normal loop. Okay. So okay, so now I have two loops. Both of these are not Mobius strip. Both of these are normal, right? So what happens when I cut this? Can I have that poll question? So what happens when I cut this loop like I did last time? Let's see. I'm going to start cutting and you guys can make your predictions. I'm going to leave some in the center so that I can cut it later at the end. Be very careful when you cut this because you might cut yourself. So let's see. I get one loop. What's the highest answer? So there is tie between first two options. Okay. Yeah. Hola. Oh. Yeah. Just get a square piece. Yeah. Isn't that awesome? You get a single loop like this. Okay. Now, what happens if I have two Mobius strip? Like if I fold it in form of a Mobius strip. So can I have the next question? So what I'm going to do is there are two ways you can make a Mobius strip. So when I attach it like this, so I can twist it like a clockwise, like this, or I can twist it like that. Okay, so that will give you like two types of different Mobius strip. It's called chirality or right-handedness or left-handedness. So yeah, so this is like a very weird, like when I did that like 2 days back, that's when I got to know about this, and I never expected to see this. I did not think that I would get. Oh, sorry, I forgot to twist it. Let me. So I'm going to give it a twist. So let me twist this one like this, or okay, actually I'll twist it like that. Okay, and this is your first Mobius strip. Yeah. I'm going to secure it nicely with the tape so that it doesn't fall through. Okay. Now on the other side, I'm going to, so last time I did this, now I'm going to do this way. Okay. And I'm going to put the tape. Yeah. Okay. Now I'm going to start cutting it. So be careful when you cut it. So what are you guys guessing? Disconnected paper strips. Okay, that. Let's see what we get. can do like all sort of fun stuff with Mobius Strip. Like, be sure to like after this talk, like Google about Mobius Strip, and they are really fascinating. So now I'm almost done. Okay, ready? Guess what? You get two hearts entangled. Do you see that? One sec. Oh, actually, I think I did it the wrong way. I have, yeah. So I had done the same thing before. So now you see, you get like two hearts which are interconnected. Yeah, you see that? Try it at home. Yeah, so I have 1 minute left. I'm going to quickly recap what we learned today. So first we learned about law of conservation of energy and conservation of momentum. And we learned about what are magnets and how is electricity created and Faraday's law and Lenz's law. And we also learned about air pressure and how do airplanes fly. We also learned about Mobius strip and what are its properties. um, there's one thing I was reading about yesterday. One practical application of Mobius strip is if you have a Mobius strip conveyor belt, that means it both sides of the Mobius strip get of the strip gets used equally. So that if you have a conveyor belt which is just like this, then outside gets ruined. But if you have a Mobius strip and it circulates, both of them, both sides of it will get an equal tear, equal damage. So that lasts longer. Yeah, so I tried to answer all the questions, but if you have more questions, please send an email to edreg@fnal.com.gov. And yeah, I thank you for staying with me. Stay curious.
Thank you so much. That was great. We do have a virtual tour of some sites at Fermilab lined up next for us. If you want, I don't know, I will ask if you can, if there are questions people might put in the
Yeah,
chat, if you want to stick around and
yeah,
answer
yeah,
some of
yeah.
those.
I'm gonna stick around and answer some of these.
Okay, great. Thank you so much. And with that, we are going to head over to Cindy Joe, who is going to take us on a tour. I'm going to be driving, I guess. So let me share my screen and we'll start with the accelerator map, right?
Yes. Hi, everybody. My name is Cindy Joe. I am an engineering physicist at Fermilab. I should tell you that I'm like extra dressed up today, not just because I'm excited about Ask a Scientist, but because in an hour I'm attending a Zoom wedding. So that's why I'm extra fancy. Hopefully you appreciate it. So, I decided that it was two things I could dress up for, including Saturday morning physics. So it's for you. So I'm an engineering physicist at Fermilab. I started out as a particle accelerator in the main control room. Those of you who have been fortunate enough to go on tours of Fermilab before, some of you may have seen the main control room before. But a thing about, so at the main control room, we monitor and control and fix and just everything having to do with all of the particle accelerators at Fermilab and the beam lines, basically everything up to the experiments 24 hours a day, 365 days a year. So what Amanda's got up is a map of a simplified map of the particle accelerators at Fermilab. I should mention that that's what I did for the first 7 years that I worked at Fermilab, and for the last 3, I've been an engineering physicist working with the neutrino experiments, and I'm also the underground coordinator of the area that we're going to be giving you a tour of just now. So I wish I could take you all in person, and that we could all put on hard hats and like go 350 feet underground and look at these amazing areas, but this will have to do for now. Fortunately, we're able to, since it is virtual, at least we can show you all of these extra pictures and things and kind of give you a better sense of what's going on. So before we go underground virtually, I wanted to show you kind of like set the stage a little bit for what we're going to see. So keep in mind what we want to do is eventually we're going to visit a place where we do neutrino experiments with large neutrino detectors that we build underground, or that we build and then put underground so that they can take their data in a more shielded environment. So in order to produce the neutrinos for the neutrino detectors, we use these accelerators. So beam starts out at, Amanda is moving her mouse so you can kind of see it, the pre-accelerator it starts as a proton beam. So we produce protons in the pre-accelerator. We actually produce hydrogen ions, but we'll get to that. We produce hydrogen ions in the pre-accelerator. They go down the LINAC and they're accelerated all along the way. At the end of the LINAC, we turn those hydrogen ions into protons. And by stripping off the extra electrons, so it's just protons at this point, goes around the booster, again, gaining energy all along the way. Keep going down the MI8 line, and then into the main injector. In some cases, we'll go into the recycler as well. And then after this gets to the energies that we want, 120 giga electron volts of energy. So I just want to say that a particle accelerator is a machine that we've designed to add energy to particles of matter. And we do this for the purpose, at Fermilab, for the purpose of high energy physics. So what we want in the end is neutrinos. What we have in the beginning is protons. And so we produce the neutrinos from the protons by accelerating the protons up to very high energy and then smashing them into a target. So here at the end of the main injector, basically we kind of go into a target building where we have a graphite target. We smash those high energy protons into it. All sorts of things come out, all sorts of particles. So remember that Einstein told us that E equals mc squared. Energy is equivalent to mass times the speed of light squared. So you have a certain amount of energy is equivalent to a certain amount of mass times an extremely large number, right? The speed of light, which is a huge number, squared is an even huger number. So basically what I'm getting out of that, if these two things are equivalent, matter and energy are equivalent, and you can get from a very, very small mass a huge amount of energy. The thing is, though, you can do it the other way as well. So if we have a huge amount of energy, which we've done using the particle accelerators, we can also get masses out of them. So we start out with, and that's like the really exciting part, is that you can get masses that never existed before from exchanging with that energy. So we've taken protons, which are pretty easy to get. We've accelerated them up to huge speeds, huge energies, and then we've sort of used the target to exchange that into new masses. So all the things that are coming out of the target are not necessarily protons. Some of them are, but some of them might be antiprotons or hadrons of all sorts. The thing that we're kind of focused on is pions, which are a particle that usually what we get is, so the pions come out and then we have a magnetic focusing horn, which allows us to select the particles that we want by the focusing horn, sort of like particles enter your magnetic field and they get bent to different degrees. And you can select out, you can bend the particles that you want so that they stay in the path that you want. And so you end up with, we select for pions, and then those decay into muons and muon neutrinos. So finally, we're getting to what we were trying to get in the whole, with all of this, which is these neutrinos. So so the pions come out, we select the ones we want, and then it takes a little bit of time for that decay to happen, and that's what the rest of this line is for. So Amanda, you can like go to the end of the NUMI line here. From the target to the detector, the first detector, our near detector, is about 1 kilometer. So now we can kind of go to the Google Maps and the satellite view. So we just have a satellite view of the Fermilab site, and I'll take a little bit for Amanda to switch screens. So we have just a view of the site, and I wanted, after I showed you this diagram, to sort of put it in context for you. If you were like a bird flying over Fermilab, this is what you would see. Just working on it. I see some questions. I'm sorry that I don't have time at this moment to answer them, but maybe some of the others will be able to answer them. And I'll try to stick around for a few minutes after to see if I can catch up on some of the questions in text. But
I was
we'll
trying to be fancy and it's not working. So I'm going to try. So let me get to the
no problem.
Google map.
Everybody following along so far? Doing pretty good? Hopefully so. So yeah, so here we have a bird's eye view of Fermilab. So everything that I was just, yes, great. Everything that I was just showing you was, you know, a diagram view. And then here we are sort of like in real life, right? So if you can zoom in a bit, Amanda, to the, you know, Wilson Hall, the main building at Fermilab. And then next to it is our LINAC, is like the building where that pre-accelerator and the LINAC are. And on top of the LINAC itself, we have a bunch of earth piled up for radiation shielding purposes. So down the LINAC, around the booster, you know, so this is what we were just doing in diagram form, except, you know, here's what it really looks like. Down the MI8 line, and then around the main injector. And you can kind of see in this picture, you can see sort of these long hills. You can kind of see the shadow on them. Those hills are, again, the piled up earth over under that is like the actual accelerator. So we're coming out here to the target service building and then out to the Minos building. We go in a straight line. We're like starting to go into the ground now because where we're aiming for is 350 feet underground for our neutrino, our near detector. So that's where we are now. So now, Amanda, if you can switch over to, so that building where Amanda's sort of like showing, now if we can switch over to the other view with the 360. Oops. Maybe restart at the, maybe just reload 360.vanilla.gov. Yeah, great. So here's the Minos service building. This is kind of like my domain. Minos, by the way, is the first experiment that we historically built this whole facility for. The name of it is an acronym. We love acronyms in physics, and especially at Fermilab. So it stands for Main Injector Neutrino Oscillation Search. The main injector is like our really big workhorse accelerator here at Fermilab these days. Neutrino oscillation search, like that's what we're trying to find. We're trying to see these neutrinos do something called oscillation. And at the time that Minos was built, we had this idea that neutrino oscillation happened. We had some sense of how it might happen, but there were some things we really wanted to tie down about like what was going on in the neutrino oscillation and really measure. So let's go into the building. And this is our shaft. So the way that so remember, like we're here at the surface, we want to end up 350 feet underground. As people, we would take an elevator. We are very safe at Fermilab. We would not do what this tour is about to do. But for the purposes of this tour, this shaft is actually like an open shaft that's 350 feet long. And this is how we get equipment down there, like with a giant crane. So for the purpose of this tour, you would not do this in real life. You would take the elevator, but we would go down this shaft in the elevator. And actually, if you look up, you can see it's a pretty deep shaft. Right. So let's go look upstream a little bit, Amanda. So in beam land, you'll in particle accelerators, you'll be thinking there's kind of like two directions that you'll often think a lot about. You'll be thinking about upstream and downstream. It's a lot like water, you know, like the protons or whatever particle are flowing this direction. And so when we go upstream from this area, we're looking towards where the accelerators are, like where the beam comes from. So let's go to that area. So if you were underground, like this is what I would be showing you. We would all have our hard hats on. I would ask you guys to take as many pictures as you wanted. So this is what it looks like. And you can see that the tunnel is, it's pretty crazy, right? Like what we've done is we've actually taken a boring machine like they used to build subway tunnels and just dug this out of the rock. So the local rock, like the shale, the limestone, and then what you're seeing is not the rock. What you're seeing is like we've put down rebar and we've sprayed shotcrete, which is like liquefied concrete over it. So you're usually seeing like the concrete itself, but we have bored this through the rock and you're seeing this really steep hill. And that's because remember, like the accelerators are a little bit underground level, but then we want to end up where the detectors are, which is a lot underground level. And so there needs to be sort of like a gradient in between. So here's like the very end in which, the gradient is starting to go down and you're starting to see like this sort of steep area. So we have to like come down pretty hard so that we can have a flat area for the detectors to be. So if we were to walk up that hill, we go more towards the area where the accelerators are. Okay, so if you scroll around, Amanda, and then we have all of these utility things, where we move around underground water and electricity and all the things that you need to do to have a working facility underground. And that's one of the things that it's my job to take care of since I'm the facility manager for this underground area. Let's go back to the bottom of the shaft, and then let's go to to the hallway. So what you're seeing around you, I want to mention that everything that you see down here, this is way more impressive when we're actually going underground, but everything that you see down here came down the shaft. So we had to have an extremely strong crane. I think our crane is 15-ton capacity. And we lower everything down piece by piece. So these big detectors that you see are all lowered piece by piece and like built in the tunnel. So if you go to the Minerva detector, Amanda, thank you. So actually, if you look a bit, if you scroll, move us around so we can look upstream to where we came from. So you're seeing all of these utilities and things that are down here. If we were down here in person, I'd point all of this out. Giant power supplies, all sorts of like really great stuff. So back this way is back towards the shaft where we came. So we've moved significantly down in the downstream direction towards the detectors. Like we've moved the path that the neutrinos would go. So the neutrinos are produced upstream. They actually come out of the rock. In fact, actually, if you go, right about there is where neutrinos will actually, the thing about neutrinos is they're really hard to detect because they don't interact very much with matter. So we have to produce lots of neutrinos and we have to give our detectors as quiet a background environment as possible so that we can like see those 1 in a billion sort of interactions that we want to see so we can study the neutrinos really well. So the thing about the thing about putting it underground is because there's all sorts of cosmic rays and other sorts of interference where if our detectors were in that environment, it would be a lot harder to see those little neutrino events that we want to see. So we end up seeing a lot of noise. So it's better for us if we can put the detector underground. And in fact, if we can go like as deep underground as possible, like all the better. So this one is only 350 feet below the surface, but the far Minos detector, which is like another detector even further downstream, I actually forgot how far below the surface it was. I feel like it's on the order of a mile, but I'm sorry that I don't have that number for you right now. It's a little bit before my time, but it's even deeper. It was at the bottom of an iron mine in northern Minnesota. And so the way that we built the detector was we had like one detector here and one detector at the end, and several hundred miles like in another state over. And we compared what we saw in the two detectors. We knew that like we had produced this beam. We knew what it was like at Fermilab because we had a detector here. And we wanted to see what it was like several hundred miles later. Like it's the same beam, but just a little bit of time later. That's basically what we're doing is we're moving distance so we can check what it is in time at this point and then in time at a later point. We can compare what we're seeing. And spoilers, actually what we're seeing is that the neutrinos change. That's the oscillation that we're talking about, is we're seeing what we produced at Fermilab as almost all muon neutrinos turn into some electron neutrinos in those muon neutrinos. And that's like the crazy thing that we really want to study. as neutrino physicist. Right. So those neutrinos, this is all a side note from neutrinos don't interact with matter very much. So we actually don't have to build like a beam pipe to carry neutrinos. They just come. They just come through the rock. They come through the earth. They come through outer space. Like you're being bathed in neutrinos at all times. It's pretty crazy. So that's kind of one of the nice things. So this great big detector that we're building at Fermilab, and in South Dakota right now, the Deep Underground Neutrino Experiment, or DUNE, is going to be like even bigger, even deeper, even like more neutrinos, just like studying this to the utmost degree. But back to where we are here in this tour, MINOS was one of the experiments that really started this all. So if we can turn around, Amanda, to the other side. Before we get to MINOS, we are looking at a front plane of, sort of veto plane, what they call it, that's sitting in front of the Minerva detector. So this facility was built for MINOS, it was named after MINOS, and then after MINOS had been running a while, these other experimenters were like, hey, we really want to study the interaction between neutrinos and matter. So if you're going to build a detector, if you're gonna you want to know what's going on with your neutrinos and with your detector and really be able to study what's going on, you need to know what the neutrinos are actually doing. Like, are they what do neutrinos do when they interact with detector materials? What do they do when they interact with rock, with water, with gases? So that's what how Minerva was conceived, and that's the front of the detector that you're seeing here. So they actually built it afterwards, but it's in front because, well, we had room and it was a good place to put it. So it's a slightly smaller detector, and it's done a lot of really great work as well. All right, so let's look, Amanda, at the back of the MINOS detector. So we would walk around, I would take you guys up the stairs, and we would look at the back of this detector. And the side and everything. So this is, believe it or not, actually like kind of one of the smaller detectors. It's a huge detector, but this is, I think, approximately 1/8 the size of the FAR detector, the big one that like is in Minnesota that we used as part of these two when MINOS was running. So so yeah, it's this huge like steel and scintillator construct. It's very heavy, and basically the way that it worked was your neutrino signal, like your particles would come in, your neutrinos would come in. If you're lucky, they would interact with your detector, and then you would get not neutrinos, but the things that come out of neutrinos when they interact with your detector, which in our case would be muons or electrons, the signs of a neutrino interaction. And there's ways to like filter out what's a neutrino interaction, what's not a neutrino interaction. But your detector is made of material called scintillator, which produces light when this charged particle goes through it. And so you're getting a read back. So your neutrino comes in, it goes like, and it produces, I'm sure it makes that noise as well. And it produces these other particles, and those particles are what you're seeing. So those particles, again, what you're seeing is the light signal that comes from those particles coming through your detector. So your detector in this case is made of steel, which we magnetize, which is also useful. And then because it makes particles of one charge go in one direction, particles another charge go in another direction. And it also means that some particles that otherwise come straight out, like stay in your detector. So you get a little bit better signal. It also, but the scintillator is really the seeing part of your detector. And so you can imagine in something like MINOS, you get like some seeing part and then some, but you can't see in the steel part. So it's really useful in some ways, but it's kind of like holds you back in other ways. It's also the way that MINOS was designed. It was really easy to see muon neutrinos, but it was really hard to see electron neutrinos. So next, we decided to design a detector called NOVA to address some of these issues. So let's go back where we were coming from and take a look at NOVA. So NOVA is the NUMMI off-axis electron neutrino appearance experiment. So we're going to go in the door here and take a look at NOVA. So nova is off axis. So where we were standing, like when we were in the hallway earlier, was pretty much like the center, like middle of the neutrino beam. This is off to the side. And they do that on purpose because they found that the signal that we really wanted to see, like in the energy band that we wanted to see, we were seeing more of the energies we wanted to see and fewer of the other neutrino energies that we weren't as interested in looking at. So we put it off axis, like on purpose. And then this detector is built with a different technology. So instead of using, we're still looking at scintillators, which produce light whenever the neutrinos interact. But instead of having like Minos, where we had solid plastic scintillator and like lots of steel, Nova is made out of plastic and mineral oil. So it's very light, and you don't end up with some of the problems with the steel. You end up being able to see like your signals actually go a greater distance, and you're able to see them sort of like in greater detail. And that was, really helpful to us when we wanted to study the other side of the oscillation, which is where the muon neutrinos turn into electron neutrinos. So NOVA really gives us a view at those electron neutrinos. So it's a little, context is a little bit hard here, but, this is about the size of something that would fit on like a really large truck. And so it's, I don't know, a few meters wide, a few meters tall. You can kind of see the stairs at the bottom, which can give you some context. And again, we have a near detector, far detector system in which we're comparing what we see here at Fermilab with what we see a little bit in time, and therefore, your neutrinos have had a chance to change later. And we have another detector in northern Minnesota, which is huge. It's a really, really, really big detector. I wish I had a picture of it for you. But it's like the size of, I think, I want to say like a 747. So like a really large plane, like an intercontinental sort of plane, or a smaller dinosaur. So NOVA is really cool, and there's still an experiment that's taking data right now. I know that Abhilash and maybe some of the others on this are NOVA experimenters, NOVA collaborators. So let's just quickly look at the back end, I guess, of NOVA. And then I think I have just a few minutes to maybe take some questions. Yeah, so, what we're seeing here, again, all of this has been designed by like really clever and really interesting people to see what we want to see. So, we have some curiosity about the world. We want to study more about like how things work. And so we designed an experiment which can help us get data about exactly what it is we want to see. But then like when we make that experiment, you can't just be like, oh yeah, I came up with this great idea, it's perfect. You have to actually make it and try it and like make your dreams reality. And that's where all of these like really cool technical and mechanical and operations oriented people like really come to the forte and come into their own and sort of like produce these sorts of things. So it's really, I think particle physics is always, sort of like a marriage between like theoretical people and experimental people, and like the dreamers and the doers, and the people who are like making the beam and the people who are like analyzing the data, and like everybody has to work together to like make any of this possible. So I think we have just a few minutes, and maybe I can take a few questions. And also, it doesn't have to be questions about neutrinos. It could be questions about like, I don't know, what it's like to work at Fermilab, or being a engineering physicist or whatever.
Thank you. That was awesome. So I couldn't keep an eye on the chat while I was running the show.
Yeah, I'm going to rely on you to sort of pick and choose a little bit.
Yeah. So you expect to see some electron neutrinos at Dune. What about tau neutrinos?
Oh, that's a good question. So, right. So there's 3 known types of neutrinos: electron, muon, and tau. And we talked about producing muon neutrinos and how some of them turn into electron neutrinos. One thing I didn't mention is that they do turn into tau neutrinos as well, but it's like you may or may not be able to see those tau neutrinos depending on a lot of variables, such as like how your beam set up, how your detector is set up. I believe, I'm not like up to the latest on what Dune's doing, but I believe that there might be some. I've heard people on Dune talk about tau neutrinos. I think that there's some way to sort of see something, but I don't think that Dune is built for like viewing tau neutrinos directly. But I think that they might be able to see like some, further, learn about some parameters that could give us some insight to the tau neutrinos.
Awesome. So we have a question. You are still tracking 3 neutrinos? Have any new ones been found?
That's kind of like a $1 billion question. So something that we're trying to figure out in neutrino physics is if there is another type of neutrino, and some people think that there is. We call it a sterile neutrino, basically because we think like from signs that it might be there, but we can't actually see it, and we think that like it doesn't interact the normal way, and so we wouldn't be able to detect it the normal way. But there's evidence based upon like the numbers don't add up. So there's evidence based upon like what we're seeing in experiments that there might be another one, but we don't quite, have the ability to announce that we've seen another one because the evidence hasn't quite gone in that direction. But it's like a really big question, and it's something that a lot of experiments are really studying. So the ones that I mentioned in this experiment line are all sort of mostly focused on neutrino oscillation, but we didn't even talk about some of the other experiments that I work with are really focused on the sterile neutrino question. And they're in like a different neutrino line. They use a different target. They're at like a slightly different energy, and their detectors are designed a slightly different way, like specifically to focus on this question of this other kind of neutrino. So great question. Any other questions about like not neutrinos or
so I know you said you have your Zoom wedding at 3, but if you don't mind hanging out for a little bit, if people, I know sometimes it takes a minute to like think of a question and put it in the chat. So if you don't mind hanging out for a little bit before you have to leave and answer some questions in the chat, that would be wonderful. And if we can have our panelists join us, we have on our panel. So we've, we've heard our talk. We've had our virtual tour. Thank you so much, Cindy. And now we have a group of panelists that work in a variety of different jobs in a variety of different areas so that you can ask questions. Not everyone at Fermilab is an expert of all things. So it's a good thing so that's why we bring together a mix of people that can answer a variety of questions for you. So bye, Cindy. Thank you so much. And like I said, if you can hang around and answer some questions, that'd be wonderful.
Yeah, it was a pleasure. Thanks for coming.
We have Alyssa Miller, who is also an engineering physicist. We have Sai Manahari, who is a mechanical engineer. We have Christina Mantilla, who is a physicist on the CMS experiment, and she is also a Letterman Fellow. And we have Gray Putnam, who is also, he is a graduate student at the University of Chicago. So it's wonderful to have all you here with us. So I said your names, but I'm going to give you a chance to kind of go around and introduce yourselves and say a little bit more about the work that you do. So Alyssa, if you want to go first.
Sure, yeah. Hi, everybody. My name is Alyssa Miller, and I am an engineering physicist for Accelerator Division at Fermilab. So to give you a little bit of context, to back up what Cindy was just showing us, that's like a great big giant detector that the experiments use to look at particles, and I make that particle beam go, sort of. So I'm responsible for the part of the accelerator complex that delivers that beam. So that requires lots of special like magnets and like passive pickup devices, like instrumentation to watch the beam so that you can confidently know like what it's doing, so that you can deliver beam to the experiments the best way that you can, and safely as well. And I used to be an an accelerator operator, and work in the main control room. So that's kind of like view from 30,000 feet, which lets me do my like very specific science on my part of the beamline. Yeah, that's what I do.
Thank you. Sai, you want to go next?
Hi, I'm Sai Manohari Kanchale. Everyone can call me Sai. I'm a mechanical engineer working in Neutrino division. Yes, Cindy showed a wonderful underground Minos, Nova detectors and all. So I contribute with actually SBND. That's another experiment at Fermilab going on, and also part of with the Dune near detector or the Argon cube. So basically, I'm a mechanical engineer. I have to support physicists for their experimental setups, be it the structures wise or building the platforms to access platforms for the experiments, or those giant steel structures you see, right? So that either installation or dismantling, how to do that, how to handle all the things. I usually take care, and I do some design analysis before we actually give anything to the production. That's my expertise. Thank you.
Great. Christina.
Hi, I'm Christina. As Amanda said, I'm a postdoc. I work for the CMS experiment, that is the Large Hadron Collider. So I'm a physicist, and most of my work consists on data analysis, both from the experiment that is at the Large Hadron Collider, and also in a small experiment as well that we're building that it's a different kind of setup, but it's also an accelerator experiment in the sense that you have a beam and then you have a detector at the end of the beam. It's not neutrino physics, but it's just similar in the sense that it's looking for new physics that is related to mostly, possibly, the existence of a dark matter particle. Yeah, that's mostly my work.
Thank you. Graith, you want to go next?
Yeah, hello. So I'm a graduate student working as a physicist on SBN, which is one of the experiments at Fermilab. It's the one Cindy mentioned is looking for sterile neutrinos. I'm basically working on two of the detectors in that experiment that are coming online, SBND and Icarus. So I'm doing some work with some of my work is like simulations of those experiments, how we expect them to work. And some of my work is actually helping to get the experiments up and running and making sure that the data's of good quality.
Great. Thank you. And so this, like I said, this is kind of the time where you can ask some questions in the chat related to the work that we do at Fermilab, related to the areas that you might be interested in. I know I recognize some current and former Saturday morning physics students on here, so please feel free to ask questions to this wide variety of expertise that we have. So one question I have is actually, I'm going to ask Alyssa. So you said you're an engineering physicist. So how is that different than an engineer, and how is it different from being a physicist?
That's a really good question. So the best way to describe my job is actually to describe what my job is not sometimes. Because, using that white space, it's valuable. It gives context. So an engineer is a little bit easier to answer for, because the engineer a lot of the time takes the time to build, for example, like a heat exchange system. And so a physicist, which is technically my title, I am a physicist, engineering physicist. But when I think about the real physicists, I think about the experiments, and I think about the people who analyze the data from the neutrino detectors to figure out what's going on there. And so I live in between, where I was saying, I make the beam go, but I make sure that it's delivered the right way. So if something fails in my beam line, I sometimes have to consult the engineers and say hey, you either didn't build this right or like it's broken and like you're the expert on that system. But I think that engineering management is like a real job title someplace, but that's kind of what I do. Like I manage the engineers and I say like, this is what this system needs. And because I get to look at this collection of systems that make up the whole beamline with the magnets, the instrumentation, the controls, the readbacks, all of that, because I have eyes on that, that gives me the ability to talk to the engineers and like get those systems individually to work the way that I need them to, so that we can all help the experiments get the beam that they need and do the analyses that we support indirectly.
Awesome. Next question is for Gray. Why neutrinos? We just saw this virtual tour of all the neutrino, the neutrino experiments that are at least underground at Fermilab. We have a lot more building, a lot more for the future. Why are we interested in neutrinos?
Sure. Yeah, so that's a great question. So I think, what I would say, my perspective on it at least, would be that neutrinos have been, for a while in particle physics, a really difficult particle to pin down. And that's because they interact very weakly. Something like, if you send a neutrino through miles and miles and miles of lead or some heavy material, it's still almost certainly not going to interact. So that's why we need to build these really powerful accelerators and put really, really big and heavy detectors inside of those neutrino accelerators in order to get any idea of what their properties are. And basically, we've started to do this, especially in the past couple decades, and it's been revealed once we've started looking more at neutrinos that, it's not just that they're hard to pin down, hard to figure out, but actually that they also have interesting properties. So one is that they oscillate, which is something I think Cindy mentioned, that there are 3 types of neutrinos and they turn into each other. And another related one is that they have mass, and some of neutrino experiments are trying to pin down how exactly that works.
Awesome, thank you. And I have a question for Christina. So you said you work on CMS. What are you kind of currently working on now? How does Fermilab connect to CMS? For people that don't know, that's over at big detectors over at CERN in Switzerland and France. If you want to talk a little bit more about that.
Yeah, so I work in data analysis of CMS, and CMS is this detector that it's basically underground in the Large Hadron Collider that is in Switzerland. So we actually get the data and it's distributed around the world. So many collaborators are like just working around the world with the data. So you don't need to be there. And Fermilab in particular has a special connection with the CMS experiment because it has a very large group of physicists and engineers that work for this experiment. In the terms of what I specifically do, I do a particular analysis of data I'm looking up for a particular kind of particles or like a specific signature in the detector. And similar to what I do, there are like 10 other postdocs in the group that do similar things, but for a different kind of signature. So most of the work that we do, when we explain it to each other, we talk in terms of how our signature looks after these proton-proton collisions that occur in the LHC. And the one that I do, or I'm currently looking for, is really the production of Higgs bosons, which were already discovered years ago, almost 10 years now. But we do not know all of these properties yet. So I think one of the big goals of the Large Hadron Collider now is really to understand the properties of this particle at the highest precision possible. And in order to do that, you basically have to explore all the possible, decays that this particle could have, all the possible production modes that this particle could be produced by. So my analysis is one of these, and I think what's interesting about it is that we're looking for this production of the Higgs boson, particular high energy. So we're taking advantage of these very high energy collisions to try to look for this data. And I think there's an effort that is ongoing. Now the Large Hadron Collider is stopped collisioning protons, but it will start soon again, and we'll have more data that then can add up. So it's something that we're always kind of like updating. Yeah, I think that's the answer.
That's great. Thank you. Sai, you talked a little bit about, some of the engineering projects you work on. What's kind of the biggest engineering challenge you're trying to solve, something you're trying to figure out? If you want to talk a little bit more about something that's kind of, I don't want to say bothering you, but something that you're thinking about a lot, trying to make work.
Oh yeah, that happened like last couple of months, like December, January specifically. Something we usually work on like steel or like a ductile materials in a broad perspective, but this time we came across some design that has been that's been out of composite materials. And usually composite materials like G10, FR4, that is being used as an electrical insulation and all in a lot of Fermilab applications, but not actually to carry some weight, which is something like a threaded rod and a nut, a huge one, but just with the fibers being cut all the way and there are no calculations. So that's kind of a big concern, like how sure are we with the design to just use few rods and carry some weight on it. So in lieu of calculations, either we need to actually do a load testing and see where it breaks, how it's breaking, or is it stable, or for how many hours, or is it for a day, and then because this is being brittle, just in case if it's a ductile material, that's okay. It will just deform gradually. It will just distort in the sense like the shape is deformed, but it doesn't give a big failure. But this brittle is just like a glass; it just cracks, and we need to hang this APA CPA planes, which are made out of wires, and they are very 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 expensive. I'm talking around like millions of dollars worth are being hanged on this one, and we really don't know. This is a collaborative work. That design is not from Fermilab because it's a collaboration work. Everyone will pitch in and do it. But in order to use at Fermilab, we maintain some standards. So to meet the standards and also that's a little challenging. So anyway, we have given that out for testing because of this COVID. We actually cannot go and work at Fermilab site. So we chose a vendor and asked them to do it, and then we got to know the threads are really strong enough. They are able to withstand the weight, but the thread has some pin connections, a huge H block and a small kind of 16 pins, and this H block which is like width of 60 and thickness somewhere around like that with the cut off pieces and all, but that broke around like 1600 pounds. So now more challenging is because it's a composite, as you know, it has two and it's a G10, it's like a fiber cloth. Okay, which direction are the fibers? Everyone, it's like a mystery. You have to find out looking at the crack, find out, oh, is this the epoxy direction, is this the weak direction and all. We don't have any clue from the manufacturer. So it's like also fail the part, bring it out, look the cross section, see how these fibers are aligned, or maybe suspect this is the strong one, this is the failure one. And it's more like also decision making, but and we don't have any spares. So now it's like also with the time and all, okay, according to the drawing, at least we have one drawing. So making sure some details are correct and the manufacturer has manufactured in the same way. It's more like decision making also, critical thinking. Everything falls in looking at what are the combinations, how to go, and what's the next step now. Build some more space and do actually the testing for a week and see what the stability in the readings, and how do you actually read when something is hanging, then come up with some other ideas of magnetic dial indicator using, pointing it to something and making sure that actually vibrates. And yeah, different ways. Or are you looking for a macroscopic level stability or microscopic level stability, and all that depends on the application, your usage and all. So that's something quite interesting. And even every one of us are learning, from seniors to like a kind of uh, a few years experienced engineers and all.
Yeah, when you said the cost, that's a lot of pressure. So
That's why we don't want to take a chance, but at the same time, we don't have time to quickly modify and come up with some other designs and all. But that's like many engineers are involved, so and it's more tough when engineers, scientists, everyone are involved to come to one conclusion, saying no, this is what it is. So engineers, they want like high good factor of safety, but as a physicist, this is what I understand from physics persons. They say no, why do we go for high factor of safety? You can just use the factor of safety like 2 or max like 3 that is usually used for ductile materials. No, 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 we cannot take chances because this is a brittle material. The fracture can happen without yielding and all. So we have to go for high, which is like 5, kind of all this. So you should be really, your attitude should be convincing, but definitely not demanding. And how do you convince? You have to have a lot of patience and dig out all the proofs, like why is it 5? So usually this is what happens in the technical things. Okay, why is it 5 or why is it 4? Why, with what standards? Or you don't have much standards with this composites, then how do you go up? Looking for different papers or do number of experiments and see what that standard deviation in those numbers. So all this mathematics, statistics all come into picture altogether. Thank you.
thank you. Gray, I have a question about a sterile neutrino. If it's a type of neutrino that maybe would not change its flavor?
Yes. So the first thing is I mentioned, right, the experiment that I'm looking for or the experiment that I'm working on is looking for sterile neutrinos. So the thing that does distinguish sterile neutrinos and what gives it its moniker is that they really don't interact, right? Like I said before, neutrinos very weakly interact. So you need to build big experiments in order to measure them, but they do interact. You can do it. Unlike active neutrinos, sterile neutrinos really don't interact at all. But they do oscillate, actually, like normal neutrinos. And that's really the only way you could even in principle see them, right? You can only see sterile neutrinos through their impact on the active neutrinos. And that is basically how this evidence, I think Cindy mentioned it quickly. There's some evidence for the possibility of a sterile neutrino that could be out there. And basically what that evidence comes from is there was an experiment, or there have been 2 experiments now that have looked at active muonneutrinos and counted fewer of them than they were expecting by like a couple percent. Sorry. That there have been a couple experiments that have seen, let's say, anomalies in their flavor oscillations. And those those anomalies would have to be caused by a new sterile neutrino.
And just a quick follow-up to that, do you think sterile neutrinos interact by gravity?
They do. So I glossed over that. They do interact with a really, really tiny amount through gravity, but that's not something you can even really, in principle, detect in an experiment, at least not with anything close to the technology we have.
Thank you. Christina, so I'm going to ask you because I heard I'm kind of selfishly asking you to share this. You're working on something that is kind of new. You're working on the design and building of an experiment. If you wanna share a little bit about that.
Sure. Sorry about the noise. My puppy's crunching. the board
It's
here.
no problem.
Okay. So yes, I think besides working on CMS, I'm working on this new experiment that is called the Light Dark Matter Experiment. I wish I would say that it's funded yet, but it's not yet. So it's more like in a what we call an R&D phase, where we're just trying to like do research and trying to demonstrate that this experiment has a potential of discovering something, and then we want to motivate people to fund the experiment. So it's called the light dark matter experiment, and you can just tell by its name that it's trying to look for particle dark matter. What it does is basically it tries to see if you get into a very, very high intense regime where you can try to produce as many particles as possible, is it possible to produce dark matter there? So it's one of these what we call a fixed target experiment. It's similar to what a neutrino would do, right? You have a beam, it goes into a target, and then you have a detector that is downstream, or we call them just in this side. And then you detect what happened in this interaction of the beam and the target. You actually have something similar at Fermilab, where you have the proton beams, and you have a target there. This experiment is used for something else. But what we're trying to do with this experiment is have a beam of electrons. So it wouldn't really be with the beam of Fermilab, but it would be with a beam that is currently in a SLAC in the Stanford lab, where you actually have a beam of electrons, you have a target, and then you have a detector here. So that's the setup, and then we're trying to actually discover with this is these possible particles that it could be the signs of dark matter. And the reason we're going to this light regime, here light does not merely stand for light, but actually in the sense that it's not heavy, is going to a regime that it's kind of unexplored. So we have explored with these high energy collisions, very large regimes of masses of particle dark matter, possible particle dark matter. And now we're trying to go to this other regime, which we haven't really explored. So maybe by exploring these lighter particles, we could actually discover dark matter. That's a spiel. I think, as I said, it's exciting because right now the design is there, but it's more like we need to do studies that concretely show that, if we build this, we'll be able to kind of expand our search for dark matter in a very significant way. And if everything works out, then we're trying to plan for building this in 2023 or 2024, which, when you think about it, is actually coming up very fast. So it's pretty exciting. I think it's a good time to be here.
Thank you so much. Alyssa, I'm also going to selfishly ask you a question because I saw you mention it a little bit in the chat, the importance of asking questions in the work that you do. As you kind of said you're like this communication piece between two different groups, and how important it is to ask those questions.
I really cannot emphasize enough the importance of clear communication across groups. And my job at the lab is a highlight on that, because you can have the engineers and you can have the physicists, and why don't we just have the engineers tell the physicists what we need, someone needs to be the glue between, and so that's me. But in all other aspects, if you're not trying to speak to someone for the purpose of understanding what they don't understand so that you can make that connection, you're just talking over them. You're just talking to talk, you're talking to hear yourself. And people do that, unfortunately, everywhere. And so communication, I think it's pretty clear when someone is trying to engage with me versus when they are just talking. And being an effective communicator, it means that you also have to be an active listener. You have to be listening for the pieces that are missing, because what I suffer from, and what I think to some degree everybody suffers from, is not knowing what they don't know. like there's so much out there in the world that like I don't know about, and I can't tell you directly that I don't know about this stuff if I just have no understand. Like it's not there in my brain. There's no piece of it that takes up space. So you have to listen for the pieces that are missing, and you have to try to fill the gap so that you can actually get this connection going, so that you can both be understood, so that you can, you know, get the answer that you're looking for, or you can get your project done. So yeah, communication is extremely important in all aspects of life, especially at a national laboratory funded by the government. We all need to try harder. Like even I could take like some clues on like how to better communicate with others, and I'm always trying to listen for those tips as well. But yeah, I mean, you're simply not going to get the best result if if one party even is not like actively listening or actively communicating. You know, it's a two-way street, period. I hope that answers the question.
Well, that was great. Thank you.
Mhm.
So I'm keeping an eye on the time and we're getting ready to wrap up. So I just want to give you all a chance to kind of share something you're excited about with your work, a result you're looking forward to, a project you're working on, something that they can kind of look forward to coming from Fermilab, anything like that. So Alyssa, I'll start with you if that's okay.
Okay, something I'm excited for in the work that I'm doing right now. I mean, the thing that I find most rewarding is when I'm able to communicate my work to others. So I'm always looking for ways to engage people that maybe don't know enough to engage themselves. I try to make my work readable. I try to get rid of as much jargon as I can, even though it sounds totally cool when you're talking to strangers out in public about like, oh yeah, I'm not even gonna go off on it, but like the language that like gets used is pretty high level sometimes, and I don't think that facilitates true engagement. So yeah, just documentation and like writing things out in plain English. That's what I like to do.
Thank you. Sai, if you want to share something that you're working on that you're excited about, something that you're looking forward to.
Yes, one, as I told you, I'm looking forward with what will be the final design for this composite materials using all that hanging a lot of weight. That's one thing. And the other thing that's going to come up, we're going to have an orgon cube detector that will come and sit near Minos, which the hall, actually Cindy showed that. That's going to come in summer. That's what we are expecting. So for that, and to use that detector, there's a lot of paperwork missing, so we need to do some testings, make sure that is qualified to the working pressures, and also that's more challenging, and I'm looking forward to that.
Great.
Yeah. Hey. So I would say in the experiments that I'm working on, the exciting thing is that the one of the detectors in the experiment called Icarus is basically coming online right now. And that's a pretty and that's a pretty exciting thing to be part of as a student. So the voltage, all the power supplies are getting turned on. They're starting to collect data from cosmic particles that are coming in, and hopefully soon after that, particles from the beam. So yeah, that's really exciting to be a part of. It's really exciting to look forward to what the data is actually going to be, since it is coming soon.
That's awesome. And Christina, we'll wrap up with you.
Yeah, I think one project is we're finalizing the design of one of the cell detectors of the experiment that I just talked about. We call it HCAL. It's like an abbreviation in particle physics detectors for like calorimeters that detect basically quarks and hadrons. And it's pretty interesting because, the experiment itself is like is actually very compact, except for this big detector, which is the HCAL. So, you know, like the other part of the experiment is like, I don't know, 1 meter or something. And then you have this big block of things that is like 5 meters. So we kind of need to optimize it to be smaller and still do the work of detecting the particles that we want. So we're try that work basically using simulation. So we just simulate what would happen in the detector and then try to see if it's possible to shorten it. And that's something we need to complete pretty soon. So I think it'd be interesting to just find out and see if we can make it cheaper in some way. Yeah.
Awesome. Well, thank you all so much for taking the time to be with us and answer questions. And I saw people, you know, answering questions in the chat, which I appreciate, and letting us learn a little bit about you and your work and what motivates you. And also thank our speaker, Abhilash, and our tour guide, Cindy, for a fantastic talk and tour. I put a couple links in the chat. We have Iron Scientist in coming up at 7:30. So we have a scientist from Northern Illinois University and a scientist from Fermilab, Brendan Casey, competing to see. They got a mystery box. It's kind of like Iron Chef and Chopped in one. They got a mystery box of materials. They had to come up with some physics demos, and and if you join us, you get to, you know, decide who is the first iron scientist. So we're pretty excited about that. I put that link in the chat. I also have a link to the next Ask a Scientist. This will be near and dear to Alyssa's heart. It's a day in the life of a main control room operator. So that'll be March 14th at 1 o'clock. So I hope to see you there too. And thank you so much for spending your afternoon with us. And we will see you next time. Bye, everyone.
Bye.